Let me just put off the break.
Sure.
Sorry for that. Music.
Oh, but I can't actually hear it. So even last time. So what kind of music do you usually listen to?
Oh, just some Hindi music
Ah,
mostly.
right. Okay. Old movie songs.
Yes, old. I like very old songs usually.
Okay.
Yeah. So they keep on running on the YouTube.
Mohammed Rafi or Kishore Kumar, Mukesh,
Yeah, that's right.
that genre. Okay.
So I just, while working on the computer, I just leave the music on through YouTube. That's a very convenient thing now.
Sure, that's good.
One doesn't need any right, records or cassettes or discs. All these things have gone out now.
True, true. It's
Yes,
amazing how they faded out. So at one point
yes.
in time,
And
each of them was so popular.
that's right. Now any music, all free.
Right.
Mm, not good for the artists.
No, I think they're somehow managing it with the copyrights and things like that. Somehow, the way they deal with the distributors.
I'm
Just
not
a
sure.
different way of dealing, I guess.
So how they deal with the YouTube? I can't understand. Every song is available. It's all free. Why people will buy this now or spend
No,
money?
no, I think most of the things that are available are typically through the original sources like T series, etc. And anybody else who tries to copy that and load it on their own site is usually the video is taken off or they are shortlisted.
I see.
And some thing goes on between them and the original owners of the copyright, and YouTube just mediates between them, and
Okay, I
eventually
see.
things are resolved.
Hmm. Well, yeah, maybe
Yeah, it
YouTube.
takes a little bit of time. Yes, there is a risk involved, but I think it's a win on all sides if they look at it from a longer perspective. Especially for the new musicians, I think it's a good opening for many of them
Right.
to get introduced to the audience, and then they can take off from there.
And YouTube makes money. It's a Google owned, and it makes enough money by advertisements anyway.
Absolutely. Right.
In fact,
Some of the
most
YouTubers are making a lot of money as well in
they,
terms of
they take
the number of views they get
what's
once they cross up to a certain level.
today. I think almost 60 to 70% of the word advertisement goes to Google. Or could be more. Yeah,
Right.
they have taken. Anyway,
I
uh,
think we have sufficient people. Maybe we can get started. Quite excited about the new course that you will start after you give the finishing touches to the certification course and sonic fatigue in particular. So looking forward to the bolted composite joints course.
yeah, surely. So I would just start my. Let me just show. Okay, I have to open up my some presentations. Okay, what happened? Okay, first I'll discuss, a few points regarding sonic fatigue. Somebody asked to clarify a few things, so I thought I'll just
Sure.
try to explain that.
I'm not yet able to see your slide.
Yes, I'm just going through the tray. Oh, sonic fatigue, share.
Yeah, sure. Go ahead.
Okay, so I think there was some question regarding the sonic fatigue when I showed some slides. So what else do? Uh, I think these are the slides which were there in that original certificate presentation. And I've got just some slides to give the feel, the way, what happens for sonic fatigue spectrums. A lot of testing work has been done by various aircraft industry organizations and NASA to determine what sort of dB labels would be encountered during the various flight regimes. There's a lot of work done by NASA. So what I have done, I just copied some figures. This one, essentially, this is the measured for high-speed civil transport work done by NASA with the help of other industries, which is published in this report reference. So this is showing for high-speed civilian transport for a sort of a aero type of a wing, and what you see various contours for the overall sonic pressure levels at various locations of the aircraft. Now, this is all based on the test data. Essentially, they simulate the test during the flight by putting the sensors, they measure SPL. I mean, they measure the acoustic response, which is then converted through a lot of, I don't understand too much of about the analysis, power spectral density, and then to the sonic, basically pressure levels. So, and then convert to OSPL, which is overall sonic pressure levels. So essentially, these are the contours for various sonic pressure levels. And as you can see, in this region where the engine is there, the highest noise occurs. It's like 151 decibels, 153, 154. So high OSPL zones, 152, 153. And as you go away from the jet exhaust, these drop. So they are lightly loaded. So the issue is now, what do you do with all these noise levels? So there are many methods available now, say engineering science data units, SDU series. And of course, in Boeing, when we were there, they have their own data handbooks to determine, based on the overall pressure levels, for any region in that panel or joint, you would try to pick up the OSPL level and determine, based on certain empirical relations, which have been well determined based on the test analysis, and try to analyze for the structural fatigue life based on the number of fatigue cycles. And usually what happens, most of the fatigue cycles for the sonic fatigue maximum occurs within about a 1 minute of takeoff region. And that itself, because the frequency of that response is 100 to about 1000 hertz. So normally what happens for the life of around 60,000 hours, say, for a typical aircraft, they will run into about 10 to the power 8 or 10 to the power 9 cycles. But they are all low amplitude cycles. And so what happens for the testing to determine reliability, normally it's difficult to test a coupon and just mechanically keep on loading at lower frequency tests. So usually for testing for sonic fatigue coupons, in order to generate the high cycle fatigue, shakers are used, which can run on the high cycles. And so that the test doesn't take much of the time. Some other idea, if one wants to consider what type of coupons could be tested, I sent this afternoon one of the test report, I think, on sonic fatigue, maybe last week, where the test data, some coupons are given, or probably that can be found in some AGARD report and SDU sheets also. Some of the slides here showing just typically how the sound pressure level SPL with octave band frequency, because this can be converted to either octave band or 1/3 octave band, the response, sonic pressure loading versus frequency. And using this one can analyze also the response. So I just wrote some, and this is for a military aircraft like a F-22 downstream, say here, reference the jet engine is there, and you can see for F-22 how overall sound pressure levels are varying as you move downstream from the jet. So it's a typical example. There are a lot of references available, and I don't think I would be, those who are interested, they can read in detail for the sonic fatigue loadings. But I just wanted to give some idea. And here, this is just I've taken from one of the NASA reports, which shows the fatigue failures and static failures for the noise levels which are created. So you can see gun blast, sonic boom, propellers, jet engines, all that. It's not very important. And this one I showed. I don't want to say. Okay. So what happens for the analysis? Just only a few points I'm trying to state, and the details are given in it. If you have the access to S2 data series, you can see. Suppose you have a panel and the noise is generated. It provides some kind of a response. The panel will be responding to the noise spectrum, and it will create some kind of a sonic pressure loading with the frequency. There will be a number of frequencies which will generate it, and then one can determine the SPL variation. Okay, now, so there's a relationship for determining what happens with this response when you want to determine the fatigue margin for the failure of the joint, or somewhere maximum stress occurs somewhere on the panel due to sonic fatigue. So you want to determine how to determine the margin. So usually one can use the procedure from SDO. So the thing is, the response, SPL is a function of RMS pressure. So what happens? The SPL is nothing but pressure applications. So it will be fluctuating pressure applied to the panel. Panel will be vibrating. It will be vibrating and it will create several modes, mode 1, mode 2. Okay. Now lowest mode natural frequency you will determine for the panel. And based on that, then further analysis, I have given the equation here. Now this is the equation given from one of the papers, but this will be in SDU data sheet also, or in AGARD report, which I sent last week. So what happens? Determine the RMS stress, because that's what we want in order to analyze the fatigue margins. The knowledge which we have from the fatigue spectrum is SPL, which is sonic pressure loading. And from the frequency calculations for a particular type of panel, like simply supported, fixed, curved, rectangular, or any type of panel, you can use the handbook or methods from either SDU or some other references or AGARD reports, determine the natural frequency. So essentially the sigma RMS stress is equal to pi by 4 delta Fn function. This is natural frequency. GP is spectral density of acoustic level at fundamental frequency. Now this is the parameter which has to be determined using the handbook. I don't have simple relation for this one, so I have not written down. This has to be determined from SDU data series for the noise that is for SPL, particular SPL. So Fn, I've defined modal damping ratio delta, and Fn is of course the natural frequency. Sigma naught is the static stress on the panel under uniform pressure. So you can determine, you apply uniform pressure, unit pressure, you can get the sigma naught. And once you know this, the main thing is this function to be calculated based on SPL distribution. So once you get this from SDU, you can determine sigma RS. Typical, I've just put up a slide copied from one of the NASA reports, which is showing the RMS strain versus the cycles to failure up to 1 E9 almost. And as you can see, so what happens? You have the sigma RS determined, from the equation for a particular either joint or a panel, fixed, curved, or anything. You supported any panel. So based on that RMS and the allowable which you have, suppose you're considering endurance limit value, and assuming this is a B basis, it's a typical one has to determine B basis and 95, 95. So based on that, suppose endurance limit is somewhere here, and if the design is based on the endurance limit, that's what normally you would do. So this is strain, suppose this is 1000 micro strain, and your RMS strain applied for the particular noise level is 800. So you have a positive margin. So that is how you will work out the fatigue margins. Now somebody asked about the temperature. Yes, temperature. If temperature is affecting in a particular region, you have the temperature correction factor or some SN curve available for the temperature effect. And that one can find in SDU using with the temperature. You can determine the margin. So this is only a general method, and it's not a very detailed procedure, but it is just to give you a feel how you can determine. Any questions? Somebody who asked a question regarding some details on sonic fatigue. Is it enough or some more information you need?
Yes, sir. I have gone through whatever you have referred. Sent us, sir. It's enough, sir. That's enough. I'll go through.
So is it okay?
Yes, sir. It is useful, sir.
So do we have access to SDU data series and ISC?
I'm not sure, sir.
Okay, NAL does have it because NAL has used this procedure. Okay.
Sir, only one small thing is when we design for RMS value, there will be some loads which will be still higher than the RMS value. Like there's a peak load, right? So that also will be automatically taken care, or?
Well, if it's a dynamic effect, what happens with the sonic one, there are two things being done here. You are analyzing one of the sonic spectrum over here. Then, in fact, there are mechanical loads coming into picture because whole of the fatigue life. What happens? The sonic fatigue occurs, say, during takeoff only, about 1 minute. And then you have a mechanical cycle with loads going on. Now, normally one would do that you have a mechanical fatigue, and based on that, you would try to determine, combining that mechanical fatigue and acoustic fatigue, the final margins will be determined. So you're right, there would be some higher loads in different cycles. So that should be taken into account.
Okay, sir. Fine.
In fact, I deleted that one of the slides from here. Let me just pull out another presentation. Okay, now. The question which you're asking is, okay, let me just show. I should have included that, but I deleted that slide from here. T. Can you see this slide?
Yes, sir. Typical fighter mission profile.
Now, say typical. So what happens here? This is a fighter, commercial. Of course, you have lots of different cycles. Anyway, it's similar thing. So maximum sonic fatigue loads occur over here. So now for aircraft life, if you just consider this, based on this only the margin, probably that's not sufficient enough because the total damage of the aircraft fatigue cycle will be the damage occurring in each of these segments And you have to determine the total damage occurring in this cycle plus the damage occurring in this cycle. And that will be the final margin for the aircraft flight. So in the next slide, I had written down this damage during a flight. D flight is equal to sigma segment I di. So di is nothing but damage during every segment. One is sonic fatigue segment, then cruise, maneuver, and all those segments together. So total damage, where di damage during the flight segment, total damage during the flight design life is 2d total equal to d flight into NDSO. NDSO is nothing but design service objective. So suppose you are designing fighter aircraft, of course, you would be designing for a 10,000 flight or 15,000 flights. If it's a commercial transport, it would be medium range, around 50,000 flight. Short range will be 50,000 flight. Medium maybe about 30, and long range maybe say 20,000 flights or less than that. So total damage will be determined for one flight multiplied by the total DSO. And then fatigue margin will be 1 upon d total minus 1. So this is the procedure. So you're right, there were higher mechanical cycles. Yes, one has to consider a full flight envelope.
Okay, sir.
In fact, this is a question was asked by EDA people also, and that is how I prepared this chart for them, trying to demonstrate, yes, when the total damage margin has to be considered for the total damage, not only this locally sonic fatigue. Okay, now, so I'll just close this and shift to now. So this, I go to the main presentation of you can see this now presentation, component fatigue test.
Yes, sir.
Yes, we can.
Yes,
sir. Okay, now, so this is what I wanted to complete last, So in order to demonstrate, because this is an important test for the aircraft, and as I had said that regulatory requirement is to demonstrate the fatigue compliance of the aircraft by full-scale test. So of course, this is a component test, which I'm showing, but in the end, I have just taken a slide from Boeing for 787 fatigue test, and we can run the video a couple of minutes just to show you from Boeing. Okay, now, so objective component fatigue test for this inboard flap test was performed. What happened? As you know, the primary or principal structural elements for the trailing edges are outboard flap, inboard flap, and aileron. And flaperon is a non-principal. So in order to demonstrate the fatigue compliance, we tested during 787 program for movable trailing edges, only the inboard flap, and demonstrated the equivalence to others. Okay, so component fatigue test objectives: no detrimental growth of BVID for 3DSO, no detrimental growth of VID, that is visible inspection, visual impact damage during 2 inspection intervals, because if you have a larger damage, you have to demonstrate only for 2 inspection intervals, not for DSOs. DSO is design service objective. That is the aircraft life for which we are designing. Verification of fatigue performance of the composite structural details and any secondary loading effects on fittings and joints. Ultimate load capability after 2 DSO. Limit load capability after 2 inspection intervals. Okay, now typical flight segmentation for a commercial transport. The flight profile is you have the takeoff, rotation, lift-off, unloaded, ground handling, taxi. This is lift-off, then flap down, departure, initial climb, final climb, cruise maneuver, gas, initial descent, speed brake application, final descent, flaps. Now, during each of these segments, there are thousands of cycles, fatigue cycles applied on aircraft. And just randomly, I've just demonstrated in this picture that during each of those segments, there would be thousands of cycles. Of course, not each cycle will create a damage. There would be many cycles, would be just very small loads, but some would be higher loads. So all that means accumulation effect during a flight. So one flight is, say, from here to here. This consists of one flight, which may have thousands and thousands of accumulated cycles for various peak-to-peak loads and different stress ratios effectively. This is all random. Now, in order to generate then the spectrums for the fatigue, there's a lot of analysis done, and I won't go into the details. How do you derive the fatigue spectrum from the loadings? However, assuming that, okay, now I've defined here, this is all random cycling structure. We define one gag cycle, which is ground air ground cycle. So equivalent, so you have the lowest stress here, the highest stress in a flight envelope, and either this point could be lower or this point could be lower. So I've just said, so gag cycle is equal to, we call this gag cycle. F max, this is the maximum point. F minimum would be minimum of either this one or this one. This is called gag cycle. Now the advantage of this gag cycle is, I'll just show you. So gag cycle is F max, FB, F minimum, FA, minimum of FA, FC, gag damage. So damage, the reason why we are defining a gag cycle, we are interested in defining, we can define, okay, the flight that has thousands of cycles creating various damages. Now what happens if we can define one equivalent cycle for a flight with the maximum minimum loading and see what sort of damage, if we have this cycle F max to F minimum based on this, what is the damage created for the structure? I mean, the damages will be at different locations, different loads or stresses are acting on aircraft. Stresses are not same at every part of the aircraft. They're all different under this flight profile. And each place has to be analyzed, joints and away from the joints, every structure. So there's a lot of effort goes into determining the fatigue margins for a structure under various loading conditions. So suppose we want to analyze this. So we determine the gag cycle, then we determine the gag damage. Gag damage occurring for gag cycle, that is we are defining say D gag. So total flight damage is damage during all the cycling during the flights. D flight. Because given all the cycles, you analyze that using a fatigue spectrum, determine the total damage. So gag damage ratio, we are defining gag damage ratio is given by gag damage ratio is equal to D gag, this damage during gag cycle, and the total damage. I should have put here D flight actually, FLT. Or the number of equivalent. What happens once we have a gag damage rate defined, then we can define the number of equivalent gag cycles per flight. The advantage of this is we want to define gag dummy ratio in order to generate the equivalent gag cycles. How many equivalent gag cycles will give me the same damage, which is created by all these thousands of cycles of different amplitudes. So this is just equivalent. This is handy in determining the fatigue margins for the structures. So I just wanted to show this one as a definition, because if I'm talking of gag damage ratio and somebody asks, okay, what is this? That's why I thought I'll try to explain. Okay, now when we are testing the component, so test fatigue loading, we have to, first is our component, of course, then we have to apply the loads. And to determine what loads we need to apply in order to test the structure so that we get the realistic damage on the aircraft part. I've shown two types of loading here. One is spectral loading, another is constant loading. So spectral loading is you try to simulate the flight spectrum. Of course, you can't simulate whole of this, this like it occurs. There are procedures in order to convert this spectrum to the reasonable spectrum for the test. And again, I would not go into the details of that. There are a lot of references available, and if somebody is interested, I can send the reference. That's a very complex procedure. Okay. So but this is representative, spectral loading and constant amplitude, where you can consider, okay, whole of the flight is represented by the constant amplitude cycling, and you test it. So full scale test, generally what happens, suppose you have a metallic part. Now metal is highly sensitive to the fatigue spectrum loading, low, high, high, low cycles. And when you want to test a component or subcomponent and you want to test for the metal, you have to apply a right type of spectral loading in order to capture the effect of the load sequencing. It's very important. However, if we are trying to test a composite structure, we can take advantage of one phenomenon in composites, that generally composites are not affected by the load sequencing virtually. Whether you're on high-low or low-high, it has insignificant effect on the life. But in metals, it can have a drastic effect, as I showed that during comet failure test when they had done, they caused the overloading effect, which gave the artificially very high life. So it is very risky in the metallic structures not to use a proper type of a fatigue spectrum. Okay, now I won't go into the too much of detail because it's a subject by itself, how you generate the loading spectrums and how you test it. Okay, so now component fatigue philosophy, fatigue test cycles approaches. There are two approaches which one can use. Life factor approach, where test cycles are LF, which is life factor, into end design. Generally, the metallic structures are tested with this philosophy that you apply a life factor like a 3 or 4 to the number of. So suppose you are designing the aircraft for 50,000 flights and you want to validate the life, then apply, say, 4 times 50,000. That means you will test for 200,000 flights and meet the compliance or the fatigue life requirement. If it's a composite structure, that strategy doesn't work. The problem with the composite structures is that it has a very large scatter factor compared to a metallic structure. So due to the scatter factor being large, and usually the factor comes out to be around 10, 12, depending upon the mode of failure. And if the scatter factor is demands the life factor to be around 10 or 12, it becomes impractical to test a component. So suppose a factor of 10 and you have 50,000 flights multiplied by 10. So 500,000 million flights. But what happens when the loading is done? In one flight, there could be 10 cycles or more cycles. So that means your number of cycles grow significantly. And the danger is that due to that large number of cycles when you are applying, the failure may occur in the fittings or somewhere else. So generally, that purely the life factor is not applied to the composite. And next slide, I'll show you. So what happens here? Say typically, this is just a typical SN curve, or a logarithmic scale, of course. So typical curve for a particular mode of failure, if it's a joint or open hole fatigue. So this is typical SN curve. And when you do the N95, 95 or B basis, then this is the design curve. Okay. So suppose we are designing the structure for N1 cycle. This is my objective, and I want to design it for N1 and S1 at the stress level S1 and my design objective N1. So what happens in order to generate this much confidence in the data, fatigue data, we have to test it. Look at this one. That means in order to get at this stress level, we have to apply N3 number of. So that means the life factor would be N3 by N1, which could be 10, 12, depending upon the scatter factor, which becomes high. So acceptable practice is, rather than applying such a large number of cycles, which become impractical for composite structures, the testing is done normally. And another thing is, or else, instead of applying life factor, you can apply load enhancement factor totally. So that means this is my design stress. I must test a structure at the level of S3. Okay, so this is my load enhancement factor, means S3 divided by S1. And this may come out to be 20% higher or 25% higher. That means you are applying a much higher stress level. And due to the much higher stress level being applied for the test, you might start failing the component somewhere, like metal fittings will go. they might fail. Some joints might fail. So there's always a risk, either in using this one or in using probably this one. The third method is apply both, partly the life factor and partly load enhancement factor. So now this is the common practice by the aircraft industry to evaluate the components, testing the components for the composite structures. So what is this? LF and LEF, combined LEF and LF, S2 upon S1 for cycles and 2. So generally, structures are tested around 2 lifetimes. N2 is around 2 lifetimes, 2 of N1. And the life load enhancement factor could be around 13 to 15%, depending upon the modes, and some calculations are done. So typically around 13 to 15%, or could be slightly higher, but you don't want to exceed too much because that will put the risk to the metallic structure failures. So this is a practice normally is used for the composites. Any questions so far on this? Anybody has? No.
Hello.
Yeah. Yes, yes, sure.
I'm Pradeep here.
Mhm.
Pradeep Sahu here. Actually, this life enhancement factor and life factor, both we have to use for the composite joints. This SN curve, what you have shown, sir, in these slides, is that the SN curve for the joints or any material? Metal.
Doesn't matter. No, this is composite. I'm showing for the composite. I'm talking about composite. But this is just a hypothetical curve. So typical, it could be for joints like a bearing, failures, composite to composite joint, or could be open hole fatigue. So one would consider various modes of failures and decide the value of load enhancement factors and the life factors. Life factor normally we want to exceed two design life. It's a load enhancement factor. Based on the scatter, we'll determine and try to see what is the dominant failure mode in our structure. Suppose we have the flaps. We will evaluate the joints, load enhancement factor based on the joints, fatigue, BVID fatigue, open hole fatigue, and then compile the information, determine what load enhancement factor we have to apply. But as I said, generally it is, rough guidance is around maybe about 10 to 15%. Say. The reason why you don't want to exceed around 15% level, because that puts the risk of the metallic structures to fail. You have the metallic hinges, and if you are overloading them, then there would be the components which may fail prematurely. So this is a balance between each of the component failures, the mode of failures, the life and load enhancement factor. So that's the thing. In a structure based on the test data, coupon test data, we try to evaluate these factors and then apply it to the component test.
Professor, suppose we want to find the the life of the fatigue life of the fuselage in the transport aircraft.
Yes.
So that suppose to start with, suppose the fuselage is a metallic material.
Yes.
And, how this diagram we have to find, sir, to find the this life of this for whole fuselage, whether we have to identify the different structures like joints and at a different location of the fuselage, you have to determine the life, fatigue life, or how this can be used, sir. Just I have some doubts.
Yeah. So the thing is, when we are doing the, say for the component, when you are doing the test, or say for example, you said only the fuselage. You have a,
Yes.
you just fuselage test you are doing as a subcomponent. Now,
Yes.
fuselage has got a very complex. There would be joints. The frames are there, whether they are bonded or bolted. If it's a metal fuselage or composite,
Metal, sir.
say
Metal.
metal. So you want to determine the life. So what happens there? Usually for a metal structure, if you look into the 25 FAR 25.571 1D, that is AC, advisory circular, it gives that guidance to determine the fatigue life of the metallic structure. I can just try, let me just show you the document to give you the feel. That's an advisory circular.
Is it, sir? That is FR 23, Professor.
That doesn't matter. I'll just go
Yes.
to the 571D. References docs. FA, AC. Because that 23 also will be similar.
Yes.
Okay, now let me go to the tray. Okay, this is the one, advisory circular, 571D, and it provides all the guidelines. Here I'll show you the fatigue guidelines for these structures when you are testing. And one has to meet this requirement. So for a metallic structures, it's very clearly written over here. So this is a requirement from the safe life point of view.
Sir, we have to do both safe life as well as the damage tolerance. Both the approaches we have to use, sir.
No, safe life. You're not doing. You're not trying to determine a safe life. Actually, it's a damage tolerance approach.
Yes.
But there's a requirement for the aircraft to be tested. The requirement is to design life for
Yes,
whether it's a metallic structure or a composite structure.
Yes.
The full component has to be demonstrated through design life. And for a metallic structure, you would do the cycling loading using the spectrum loading. So you have to decide about the spectrum loading properly and run for 2 design lives. That is a requirement.
Excuse me, sir.
Yes.
Sir, this spectrum loading we have to find from the mission profile of the aircraft, right, sir? Professor?
Yes, it is. It is a mission profile which has to be analyzed. And it's not easy, actually. It's a very complex method which Boeing uses. So,
Sir, Professor, can is it possible to get from the literature any reference, Professor, to find the load spectrum best? I have the mission profile, Professor. I want to determine the load spectrum.
yes, I can send you the reference. There's a full one STP, ASTM STP written by Mr. Watanabe. He was a Boeing employee, earlier Boeing engineer. He had done a lot of work, and it's in public domain because he was editor for that ASTM STP. And I'll send you that paper also. I think I copied it. Whether I have the hard copy, which I think I might have done the soft
Yes.
copy. Or
Shall I give my email ID, Professor Dinesh Kumar sir? He'll be.
I can send it to Professor Dinesh, and then he can send it to you. Or you can put on the server. You can download.
Yes.
So,
Okay.
and I think NAL also was working on the mission profile. I think I don't remember the name of the person who was very much interested to continue the work in a mission profile. The issue with the mission profile is that those references which are there, they
Yes, sir,
talk in general, but what happens when you try to look into the nitty-gritty of that exact method, they don't provide every detail. Because suppose the Boeing is there, Boeing has their own internal method developed, and they're highly secretive. So even when I was at Boeing, we were not allowed to know the procedure. And what happened? They would say, okay, from this company here, we have to send the data. They would analyze, but they won't give the procedure to us.
Yes.
So they're very secretive.
Correct.
But in general, I'll send you the references, and probably you might get some feel. But yes, you are right. This 571D, it provides the guidance for the safe life, for damage tolerance, as if you look into that FAR requirement, it's a 2 design lifetimes for damage tolerance. And
Yes.
then it's a widespread fatigue damage. There should be no damage occurring during that time.
So what do we do, Professor? We'll find the critical component in the fuselage. Okay, 1 or 2 critical components, and we'll do SN SN approach, find the life, as well as crack growth study also we'll do for the damage tolerance analysis.
Well,
And,
damage tolerance analysis you have to do for each of the part over. There would be a lot of analysis because for different fasteners, you have to consider how much is the minimum crack length assumed, and then determine, calculate the widespread fatigue damages if it occurs.
yes.
So of course you have to cover all the critical, you can just highlight some zones where the criticality is there and try to analyze the structure. This is again very involved procedure by the industry. Once again, say the Boeing has got its established procedures over, such a long period of time. They have the handbooks, computer programs, hundreds of people working in that group, the fatigue and damage tolerance, and they do all that work. So
yes, Professor. We have also our aircraft program for which I am actually responsible for determining the load spectrum for fuselage.
okay.
So that's what I am from NL, Professor, and Professor Dinesh Kumar happened to be my teacher during my PhD at IAC.
Okay, so last year, when I had given the lectures to NAL, did you attend or no? You didn't?
Yes, I have attended actually a couple of lectures of yours, Professor. Yes.
Okay.
But on fatigue, you had not. I'm not sure whether you had given, Professor.
No, I was talking actually. There was a question coming from. I'm trying to recollect the name of the person, Lokesh or who was the person? He was very much interested in developing the fatigue spectrums. I will try to see. Maybe you could talk to him. Yeah. So, yeah, let me see what I can do,
Was he Lok Singh? Lok Singh by chance?
I don't remember actually. I can look into the email, but it will take some time and I'll send you later on the information. Okay.
Sir,
Yeah.
Professor, can I give you my email ID? I will send you one email, Professor.
Yeah, you can, you can
Yeah.
send me the email. You can send the email to me and then put your queries. I'll try to answer it.
Okay, Professor. I think it takes more time actually to have more discussion on this FNDT. So I think,
Yeah,
sir, we can.
it's an important subject. It's a good area.
Because I am responsible for that, so that's why I thought I can have a discussion with you.
No,
But
that's good actually. I enjoy it. So I'll try to help whatever I can.
if I can get some references, then I
Yeah,
can.
I'll send you the reference.
Yes, Professor.
And the STM STP. And in fact, that NAL, that the engineer who has asked the question, I don't remember his name, but he had that reference. So I will send the name of the individual you can contact.
Yes, Professor.
Okay, now
Okay,
let me
Professor.
just close this. So let me go to the.
Yes.
Hello.
Hello, yes.
Sir, good afternoon. This is Samanvay. I'm PhD student in aerospace department.
Sure.
Sir, you told about life factor. So, as far as I understood, first we do some coupon level testings, then we find the load factors, and then while doing the component level testing, we use these load factors, right?
You can calculate both life factor and load factor from the same coupon.
Oh no, I'm talking about metals, not composites.
Okay.
Okay, sir, what about when we do the damage tolerant design and there we calculate some fatigue life using the famous Paris law using sigmoidal curves?
Well, the
So,
damage tolerance doesn't use this curve
okay. So
because
these,
there you need the
yes,
dA by dN, like Paris
yeah,
law, dA by
yes,
dN charts.
yes,
This,
sir.
so stress intensity factor. This is when you are trying to use the endurance limit approach, then
Oh,
this is useful. Otherwise, damage tolerance uses only dA by dN.
yes, correct, sir.
That is in Paris region, na?
Yes,
Yeah,
yes, Paris law, classical. And then, of course, you apply lots of correction factor like accelerated, crack accelerating or decelerating, depending upon the cyclic loading, compression, tensions, overloading. So again, there are a lot of factors going into that. And in fact, there's a publication written pretty good by one of the Boeing engineers published. Mr. Goranson used to be chief of Boeing in DS, our damage tolerance approach, and he had published some papers. If I have some publication, I might send you. Interesting. Because what happens, just a Paris law, then there are a lot of correction factors which have to be applied in order to determine properly the life using dA by dN approach, which you don't find
yes, sir.
normally in the books. What happens with all this, industry develops a lot of methods, which of course is not to public domain.
Professor, for the aircraft structures, you have to use high cycle fatigue. All the components will see the high cycle fatigue, na? Or any component will see low cycle fatigue in the whole aircraft structures, fuselage or wing.
Well, the thing is, you are talking of this fatigue life. Now, when the spectrum is done, loading spectrum is divided into various segments. And what happens, you have to plot an accidents chart. and some of the low cycle or high cycle, depending upon the effect of those cycles or the stress levels, they are cut off or truncation. That becomes another area. In fact, I could talk about it later on if there's an interest. The fracture mechanics,
Yes.
but that itself is a different subject of determination.
So normally we will assume for the whole, suppose say for example fuselage. In fuselage, all the components will see only the high cycle fatigue, high cycle load. Correct, no, Professor? Because it is almost 10 to the 6 or something more than that cycles.
No, it's not that simple. Let me tell you that. I think what I'll do, I'll send you. Look into some papers from the NASA reports, some papers by Newman. I can send some references, and probably it's a good idea to read those couple of papers of considering the truncation of the cycles, how you determine which cycles are important, which cycles are not important. Because naturally, if there's, you can't test the aircraft for something like 10 million cycles.
Correct.
So what happens, some of the cycles will be of a very low amplitude. Try to ignore them if they don't affect the fatigue life.
Correct.
Similarly, on the highest stress level. So there's a cutoff method applied. Even if you read like the fracture mechanics book by Broik, element effect, it defines the procedure based on the accidents chart. So this is a classical method which is available for a long time. And in textbooks is given in the fracture mechanics textbook like David Broik's book.
Yeah.
But I will send some references which might help you.
Okay, Professor.
It's interesting.
Yes.
Okay, next one. Okay, fatigue test article. So we are talking of, say, inboard flap fatigue test over here. Basically, for this flap testing, we use this method and the constant amplitude loading rather than the spectrum loading. And of course, I won't go into the details why we chose that. So the article, fatigue test article, was created with all the damages which we wanted to study, BVIDs, VID, and to determine a particular life. So I'll go into the just a spec, the test flow. Say test article with production anomalies like BVID and undetectable damages like disc bonds. Mounted on the test rig, then of course a strain survey just to verify that all the systems are working okay, strain gauge is working okay, and then you start the fatigue loading. So here we consider, say, 2 DSOs. 1 DSO, then you stop the test, visual and NDT inspections. Then again you go to another DSO. So this is the requirement. So basically, FAR requirement is for 2 DSO with the appropriate load enhancement factor. So we tested this for 2 DSO, 2 design service lives, with an appropriate load enhancement factor. Because we were not applying a spectrum loading, so we applied the enhancement factor. That was the reason. In order to generate PVSL life. Then we loaded to ultimate load, or here static limit and ultimate loads, in order to verify after 2 DSO that we still have the residual strength available to the ultimate load carrying capability as per the requirement. Then we introduce the visual damages. Visual damage, slightly larger damage, like an impact using a 4-inch impactor, say, and visible, like a visible damage which is easily visible during walk around inspection. Then the requirement is to load it to 2 inspection intervals. Load it 2 inspection intervals. Then of course, the requirement after this is to limit load. So it was loaded to limit load carrying capability to see any damage or damage this VID or visible damage grows or not. Then static. After that, we loaded to the remaining cycles. Now, we loaded it to the 30 ESO, the remaining cycles, just to be conservative, but it was not the requirement of the regulator. So that is how. So essentially, it was loaded to 3 DSOs. And then, of course, NDT and tear down inspection. We found no damage done to the structures anywhere. And that is how, using the fatigue test article, the compliance was met for the fatigue test for this. This is just showing the flap, which is similar to the static test. Okay, so inboard flap fatigue test summary. Inboard flap fatigue test was successfully performed without any damage growth. Design service objective were met. Based on inboard flap fatigue test or other MTE structures were validated to meet the regulatory requirements. So that is how it was completed. Okay, now this completes the 787 movable trailing edges discussion regarding the certification process. So that is the end of this. And then I have just put the requirement for the full component test. Of course, this was not done over here because it was not our responsibility. We were only for main movable trailing edges. And this is, of course, headquarters like Boeing Seattle, where they had to demonstrate the compliance requirements for the aircraft by testing the full-scale aircraft. So it was done in Seattle. And this is, I'll just, for a couple of minutes, let's see this video.
So it's not playing.
Oh, it's not, sorry.
No, we are not able to see it.
So how do I make it? Does it go to the presentation?
You will have to share the browser or the wherever the YouTube is playing.
Okay.
Instead of the slide.
Is it okay now?
Not yet.
Nope.
So how do I see?
You have to share that screen where YouTube is playing.
Okay, let me see now. I don't see on my screen. Share. Are you able to see
Yeah,
now?
yeah,
Yes.
yeah.
Yes,
We can.
Okay, so I think I'll
Thank you.
start from beginning again. How much is deflecting the wing?
Is there any sound with the video, Dr. Garg? Because we are not able to hear.
Pardon?
Is there any sound along with the video?
No, there's no sound.
Okay.
This is the only sound, the music which is playing, that's the only sound.
Sure.
Can you hear some music? That's it. I think this one can be stopped now. So essentially this okay. So you saw the wing, how much? Oh, sorry, this it started running some other video. So basically, you can again watch on YouTube. You have the reference. You can go to Boeing website, static testing, fatigue testing, and you saw the wing, how much is deflecting? Around 26 feet during testing. Okay, now this finishes the presentation of this certification lecture. Are there any questions on this one before I close this?
Hello, Prat.
Yes.
For the for fatigue design, is it mandatory FNDD design of the any of the fuselage structures? For example, is it mandatory to do the full scale test at the full scale level, or only we can do analysis and some components we can do the tests?
Okay, now it's a good question. Can you see the screen?
Yes, professor. Yeah.
Okay, now read this requirement, and there's a mandatory requirement from FAA that full-scale fatigue test of the aircraft has to be done. As you can see, The airworthiness section of the instructions continued airworthiness required by this must specify that no airplane may be operated beyond a number of cycles equal to half the number of cycles accumulated on the fatigue test article until such test. So current regulations require the full-scale fatigue test of aircraft, and this is mandatory. Now, if you look into this diagram, which I showed in damage tolerance, let me go back. This diagram, history of important commercial aircraft failures and resulting regulations. When the Aloha aircraft failed, then the requirement of widespread fatigue damage came up. And then FAA imposed a requirement that the full-scale fatigue test is required. So FAA will not approve any aircraft design until the fatigue testing has been shown. They won't certify because, as you can
Hello,
see,
sir.
yeah.
Sir, is there any certification for thermal fatigue?
Well, thermal fatigue, normally what happens, for the temperatures, you would take into account the effect of that during your detailed design. But full-scale testing is not done for thermal, for commercial transport, or even the military aircraft. What happens for this thermal one, the environmental effect will be shown for the component design when you are doing detailed design by the using the coupon test data. Suppose we are dealing
Hello?
with, I showed you the inboard fatigue test. Inboard fatigue test.
Breaking, sir. I could.
Pardon?
Hello, sir.
Yeah.
I couldn't hear you. Your voice was breaking. Can you repeat it, please?
Yeah, what I'm saying, full component tests are done only at the room temperature. But environmental effects, when you are doing, they are considered for your detailed design of the structure when you are doing. Say, for example, we are showing inboard flap fatigue testing. It was done at room temperature. The static testing also was done at room temperature. But you would ask me the question, the operating conditions for the composite materials, because composite materials are highly sensitive to the moisture and temperature. So how do you determine?
Yes, yes.
Okay, now
Yes.
I had explained the philosophy of certification. Certification is by analysis, verified by test. So remember these two words there. Certification by analysis, verified by test. Now, what does it mean? When you are certifying these components, you are trying to certify by analysis. And analysis methods are being verified by the test. And as I explained, say when you are talking of the verification of test, the component test is done at room temperature, and basically what the information you get, say inboard flap test, this was done at room temperature. And when we are trying to verify that the analysis is able to predict the structural behavior, and this is what you do. You test in order to simulate the prediction of strains by your FAM method and match it with the test data. So you would have, say, hundreds of gauges on a test component. You are testing at room temperature. You determine by test the strains and then verify that your analysis is also able to predict the strains. And as I explained to you, we had to match the predicted strains with the test data within plus minus 5%. And there was a lot of work done in order to refine the model, in order to generate the same strains. So that means you have got enough confidence now your analysis method. Okay, so once you have verified your analysis method, then you don't need to determine the test data in order to determine the final margins for the static or fatigue. So what you do now, I know my prediction of a strain of, say, on a skin, somewhere on the skin. Say I pick up this point here, my analysis is predicting 2000 microstrain. Okay, I use that 2000 microstrain because that is a strain which I'll get from the test also. What is my allowable? Say room temperature allowable for a coupon based on the coupon at room temperature is say 5000 microstrain. But with the hot wet condition, it's a 4000 microstrain allowable. So what happens now, in order to define the margin, you would use the 4000 micron as allowable in order to determine margin. And that will give you that environmental correction factor because you are using the allowable based on your environmental correction factor to consider the hot wet condition or a cold condition. And the failure mode, if it's a bearing test, bearing failure, open hole fatigue test, or BVID, or tension, different conditions. So environmental considerations are satisfied by the analysis based on the allowables developed for the temperature. Yes.
Sir, that environment correction factor, how do we determine that? By using some tests only, na? Or
yes, surely. Yeah. They are tests for the coupons, but you don't test the component.
Yeah. This is what I was talking about, sir. So there, yeah. Okay, I got it, sir. On coupons, we do
look in the test matrix when I discussed here, say, like a typical allowables test. You are testing modulus, tension, modulus in the stress, multiple batches, test condition, cold, RTA, hot, wet. So what happens, the knockdown factors of environments, they come from the coupon test data.
Yes, sir.
And got that is how you get the confidence and you apply the correction factors using the environment, and the testing of the component or subcomponents, large components will be normally done at the room temperature.
Yes,
because the philosophy, if you're doing a point design approach, then you have to test with the environment, by the way. So there's a difference. But if you are doing the certification by analysis verified with test, then you do only the room temperature test for the component. So it depends on the philosophy of certification. Any other question?
Sir, you mean, Professor?
Yes.
You mean allowable will take care of all the environmental effect. We don't have to do the analysis or test, other than the room temperature.
Well, when you are analyzing the structure,
yes.
If it's a metal to composite interface, you have to consider environmental correction factors or environment for the analysis. Because what happens if there is an interface between the metal fitting and the composite? You have the fasteners, then, and the operational condition is a cold or thermal, higher temperature. So naturally, the coefficient of thermal expansions for the metal and composite is different. Correct. So due to the temperature increase or decrease, they will create thermal stresses which will be on the joints. And that is where we would try to determine the thermal stresses effect on the joint loading.
Correct.
So yes, you are considering an analysis where the interaction of the metal to composite occurs. But if it's a composite to composite only, there is no thermal mismatch.
Okay.
So I think the next chapter which I wanted to start, the bolted joint, may not be starting today. It seems now only 5 minutes left or 10 minutes. So if there are more questions on this, we can discuss that. Certification issues.
Hello, Professor.
Yes, yes.
Actually, for metal fatigue, actually we have different analysis tools like MSC fatigue and all that. So, Professor, have you come across for the composite fatigue any tool, sir? Any such tool?
I'm not sure which tools you like to know, but say in composite fatigue when we are doing, based on your spectrum loading when you apply.
Analysis tool.
Yes.
Yes.
And say you would determine the maximum fatigue stress. So suppose for the composite, my maximum fatigue stress based on the spectrum analysis is particular amount of strain, which will be in the maximum operational fatigue stress or strain. Using that maximum strain level, which is like a gag cycle, and that determine the gag damage ratio. You represent that damage ratio, determine the number of cycles for the life of the aircraft and the maximum stress. Using that maximum stress and the number of cycles, and then using say ascent curve, I think tried to show you the compliance for the fatigue when we are trying to determine for composites. Let me see, yeah. So here fatigue, am I sharing this? Can you see this presentation or no?
Yes, yes.
Okay. So fatigue to compliance philosophy for a composite is no damage growth. Manufacturing anomalies will not grow, visible damage will not grow, okay? Substantiated by subcomponent component test. What happens we use the endurance limit approach for the composites. The reason being the damage tolerance approach, like a crack propagation rules are applied for the metal. In composite, there's nothing like the Paris law phenomena. You can't determine. The damages don't propagate like in metals where a crack goes. So it's an indeterministic approach, whereas in metal it's a deterministic approach. So in composite, general philosophy is to endurance limit approach. So what happens here, endurance limit approach? You have say typical fatigue spectrum. Based on the spectrum, I know what is my maximum stress. Determine the gag damage ratio, as I explained to you. Based on that, suppose gag damage ratio is 0.5. That means one gag cycle is creating about 50% of the damage created by the total fatigue cycles in a flight. So suppose my life which I want to design the aircraft is 50,000 flights, and 0.5 is the gag damage ratio. So that means I require to analyze it for 100,000 cycles. Okay. So you can determine SN curve and try to put your point and determine the allowable stress for 100,000 cycles and write the margin. But generally what happens in composite, we use the endurance limit approach. So we work out, okay, what is my gag cycle stress, the maximum operational cycle basically, and the minimum. Based on that, the stress ratio will be determined. And then using that endurance limit approach, if we are using, we have the SN curve generated for a particular mode of failure. If it's a joint, for the joint, for a open hole fatigue, that, and then normally we define the endurance limit as a 1 million cycle. So you have a SN curve, which is B basis and 95 based on the test data generated. And then this is my allowable stress or strain. Using this allowable and applied fatigue design load or the stress F fatigue, I'll calculate the margin. That is, F fatigue is less than F endurance, and that's it. This is my compliance process, which is a no damage growth based on the endurance limit approach. So this is a general approach. But if suppose what happens using this approach, your margin is negative, you find that is too conservative, then you can assume, okay, I have this, my stress level applied during the fatigue, some F fatigue, and I require the life only this much. So probably I can calculate the margin based on that. That's another thing. But this is a very conservative approach. Is that satisfactory to you? This is what it.
Yes, Professor. This endurance limit approach, you mean SN approach, right?
Yes, it is SN approach. It is. This is SN curve.
And this is for constant amplitude loading. This SN curve. This is for this one constant amplitude loading having
it's a constant amplitude. Yes, constant amplitude loading. Constant.
Stress ratio -1.
Yeah, well, stress ratios -1. Usually we generate the curves for as -1, but what happens sometimes that becomes conservative, and then we try to see if we can apply the proper spectrum, a bit, because R equal to -1 gives the lowest curve.
Yes.
It's the most damaging. So generally try to use R equal to -1, but in some cases, if the margin is negative because it's conservative, then we try to look into, okay, are we very realistic? Whether R equal to minus is realistic, are we being too conservative? Then you try to look into maybe R equal to -0.5 or -0.7, depending upon the design considerations. So there are a lot of different mechanisms available, because initially you would be conservative, but later on if the conservative is too much and you are increasing the weight of the structure or margin getting low, then you will tweak the figures.
Suppose load spectrum is there, then we have to use the minus formula in this composite also.
Pardon?
Suppose load spectrum is there, because this curve is for constant amplitude loading, Professor.
Yes. Now, so what happens? It is the way the curves are generated. There are some correction factors which, say, Boeing would have generated correction factors if we are testing a coupon using constant spectrum, constant fatigue loading, constant amplitude. But then we apply, in order to generate this 95B basis curve, the correction factors for the spectrum loading. And also the component factor. So you are testing the coupons, but what happens, large component may behave differently. So generally what happens, the company has got the factors based on their lot of test data historically. So they specify, okay, this much of the correction factor in order to bring down the curve from the coupon level so as to behave like a component. And then also we apply the correction factors, say coupon, suppose there are two fasteners which are in a coupon being tested. But aircraft may have the similar stress level for about 20 joints, fasteners, in a series of fasteners, similar stress level. So that is another correction factors we apply in order to generate the data so that we take into account the component factors. There are lots of factors. It's not that simple. In order to generate this, you have tested a coupon, but converting the coupon data to the component level, lots of factors which are applied. So typically what happens, if I have the coupon level curve, basically it will come here, typical test data. And then using lots of correction factors, it's pushed down to this level. So you're right. The spectrum loading, the component different behavior, all those correction factors are applied in order to generate these ascent curves, and then margins are written. The thing is, the companies have done work and they have all proprietary information which is not in public domain, what sort of factors could be applied in order to determine. So the only thing which you can do, okay, conservatively, you can assume some factors and apply based on maybe some references if they are available. But usually industry is very secretive always. They don't provide all the information. Is that satisfactory? Hello?
Yes, sir.
Hello, Professor.
Yes,
Hello,
yes. Yes.
Is that in the open literature, would there be availability of any, this such correction factors, Professor?
I doubt, because they're all proprietary items.
Okay.
I would try to look into if I can find, but it's very difficult, those factors. Industry doesn't part away with those factors. I can't tell you, unfortunately.
Yes.
We are all bound by our agreements.
I was searching for some such literature actually. I didn't find much information.
No, nobody will give, because suppose Airbus or Boeing, they would have generated proprietary information, they won't disclose it.
Yes, yes, yes.
And what happens for a university to develop such a data is very expensive. Because these companies spend millions, hundreds of $1 million over last, say, 100 years working. They have generated enough information from the past experience and the service failures. And that is how Boeing generates, the Boeing and Airbus. In fact, they don't share between themselves. Each industry keeps the data with them. So these factors which are determined, they have been developed over the years using all accident data. Let me tell you that. The various failures occurring in the aircraft, failures, and then they have generated these factors. Enormous amount of efforts have taken. So that is because the industry is very careful by using the factors. Those factors are based on lots of experience because they don't want the failures to occur. They would rather be very conservative than optimistic. So unfortunately, it's very difficult to provide the guidance on various factors. The only thing you can do is be conservative.
Yeah, to be conservative, we need also some factor, na, Professor?
Yes. Let me see what I can find from literature. If there is some factor somewhere
Sir, it looks
available.
like there will be some. Hello?
Yes, yes.
Sir, it looks like there will always be some gap between academia and industry. Because whatever we do, how much we develop our theories, whatever test we do, ultimately at the end of the day, there are some factors which we don't know.
Yes. Let me tell you, in Boeing side, when I was there, Boeing doesn't trust any data from outside sources at all. Every data is generated internally, let me tell you that. Every method is generated, verified fully. They do not use any method. All these methods are, of course, published, handbooks are available or the equations and all that. But everything which is used by Boeing is validated. Every equation is validated by their test data. So a strict regulation Boeing has.
Yes, sir.
So they spend a lot of money because it's a big company. They have resources to do it over years of research work done. So it's very difficult. Of course, universities can't afford that. They can't generate data. So yeah, I'll try to see if I can provide some information from the public domain. Any other question? It was a very interesting discussion about the fatigue. It's an important area.
Yes, Professor.
Okay, if there are no questions, then I can close.
Sure, Dr. Thank you.
It's more than 10 o'clock now because we have shifted by 1 hour.
Oh, I see. Okay.
So,
okay. So should we continue with this 3 p.m.? Is that fine with you?
well, it's fine with
you?
me. If you can shift to 12 o'clock, I would be better. But if you think that students are busy, then.
Okay. Do any of you have any issues shifting it to 2 p.m.? Those who are here, at least, still?
No, sir.
Okay.
No issue, Professor.
So it's okay. Then you can shift to 2 o'clock.
Sure. So we'll meet on Thursday at 2 p.m. then, IST.
Yes. Okay.
And, we'll start with a new course, I guess.
Sure. Okay.
Sure.
Good night.
Thank you.
Thank you. Good night.
Good night.
Thank
Bye.
you. Thank you, Professor.
Bye.
Thanks to everybody in the audience as well. Bye-bye.
Thanks.
Bye.
Thanks.